Asphalt, also referred to as bitumen, is a highly viscous, liquid, or semi-solid form of petroleum found in both natural and refined states. In 1896, New York City officially adopted paving, replacing the more traditional wood, brick, and granite blocks. The advantages to this move were great, providing easier installation as well as a smoother ride. Prior to 1900, almost all asphalt used in the United States came from a natural source and was imported from Venezuela. The earliest production for asphalt pavement involved the heating of an aggregate in an iron pan, and then slowly pouring the hot bitumen over the top while mixing. Between 1934 and 1937, more than 4/5 of all the highways installed in the United States used asphalt. A large boom in asphalt production and technology came around the time of World War II as well, as government agencies sought to produce a material that could allow airplanes to carry heavier loads. As the demand for asphalt grew, the refineries and mixing came to be viewed less favorably, as size, sight, and smell of the plants became a nuisance for some. These issues, combined with the great concern for air pollution in American culture between the 1950s and 1970s, caused a big recycling push in the asphalt industry. Over the last several decades, the use of HMA has become more prevalent for runway use, as it provides a smoother takeoff and landing, while at the same time reducing the need for constant upkeep.
Why is asphalt so important in everyday life? 85% of produced asphalt is used to make roads, which affects just about everyone on a daily basis. Even though all roads may seem similar, they can have very different objectives and must be designed accordingly. Two details are taken into account when planning roads, and these will affect asphalt production. First is the current traffic that travels on the road. Second is the projected growth of traffic during the lifetime of the road. For each type of vehicle, tests determine the strain that is applied to the asphalt. It is important to detect which vehicle uses the roads because the strain caused by a 5-axle truck is equivalent to the strain caused by 1,600 passenger cars. The strain is extremely difficult to accurately predict because details such as whether trucks are filled or not and the pressure in tires cannot be determined. New highly pressurized tires can increase the strain tenfold. An increase in traffic during the lifetime of the road is expected, but is difficult to tell by how much. Over time, the use of trains has declined in favor of road usage.
While asphalt is a great material, it still has many limitations that restrict its usage. We'll start with temperature, an unavoidable element that wreaks havoc on asphalt. At high temperatures, asphalt becomes very soft, leading to the possibility of ruts forming. At low temperatures, asphalt is prone to potholes and cracking. This is because it becomes very brittle at these low temperatures.
The processing of hot mix asphalt is dependent upon a chain process of curing, refinement, and mixing. In the process of creating asphalt, 3 crucial factors are taken into consideration. These 3 factors include the consistency, purity, and safety of the material. And in order to do this, the entire process requires proper structural design, mixed proportionality, and good construction. To reach this favorable end state, material scientists and engineers have concluded that the most ideal asphalt is that created out of the byproducts of crude petroleum. With this said, because each petroleum plant is slightly different in the manufacturing and processing of oil and where the oil comes from, asphalt composition can differ slightly from one refinery to the next. However, the general processing and reaching the end state of asphalt requires a general heating and refinement process, which consequently leaves the densest hydrocarbons to later be used in what we presently use in all products of asphalt today. Crude oil goes through a multi-stage process of heating, distillation, chemical processing, and once the final bitumen polymer is removed, it undergoes a process called fluid catalytic cracking, which breaks, molds, and combines individual change of carbons, consequently creating a desirable end mixture of asphalt, which is rated at different performance graded binder ratings. These performance gradings are the end description of the type of amorphous polymer that is created. Today, many different additives are added to the bitumen blend, which enable different physical properties, whether that be stiffness, viscosity, or strength. This combination to what will be the final product of asphalt then undergoes many stages of strengthening. Our common term of asphalt today is actually a misconception in that the view that asphalt used on roads is a heterogeneous mixture of natural aggregates and the chemical material of asphalt. In order to change the properties of the infrastructural compound engineers are experimenting how the separate components of asphalt combined in different ratios alter the physical properties. However, before we dive into the chemical reaction of asphalt and other chemicals, we must first understand the principal components that make the base material. Asphalt is primarily composed of a complex mixture of hydrocarbons, which can be broken down into two structural categories: asphaltenes and maltenes. Asphaltenes are a type of aromatic hydrocarbon ring that have the basic combination of carbon, hydrogen, oxygen, and sulfur. These carbon chains exist in molecular weights ranging from 1,000 to 3,000 grams per mole. In contrast, maltenes, which can be broken down into two further subgroups of resins and oils, are smaller chained hydrocarbons which are saturated and have a linear or branched molecular structure. The colloidal polymers mix together to form different grades of asphalt, which consequently change the physical properties. Both of these are byproducts from the crude oil refinement and therefore have little crystal structure. The polydispersed oil mixture consequently leads to different types of modified asphalts, and therefore the ratio to polar and nonpolar light and heavy polymers are factors that are primarily responsible for maintaining the stability of the asphalt. Due to many microstructural limitations addressed earlier, chemical substances and modifiers are added on in order to effectively eliminate any structural deficiencies. Many of these modifiers are being developed to control cracking induced by water, stresses caused by traffic, and other environmental impacts. According to NAPA, the mechanistic empirical design of HMA asphalt has to take full evaluation of reliability rather than addressing an overall approach in order to ensure long-term performance. Consequently, densification, permeability, and stiffness are all aspects to which microstructure must be modified in order to maintain structural dependability. Several polymers are used nowadays to modify asphalts, and each one fulfills different properties according to their associated physical properties. For instance, the ethyl vinyl acetate, EVA, produces high rigidity as a hard plastic material, thus classifying it as an elastomer.
It has already been addressed that asphalt varies very much with temperature. However, the chemical structure and mixture consequently has created many desirable macro and micro properties. The stiffness of asphalt is very dependent on temperature. When determining how much asphalt to mix with aggregate to create roads, the climate must be taken into account. The elastic modulus of hot mixed asphalt at 0 degrees Celsius is over 90 times its elastic modulus at 50 degrees Celsius. Higher temperatures drastically decrease the stiffness of asphalt. As a result, much more asphalt should be mixed into roads in areas with warmer climates.